What's up, y'all? Back again. We're going to continue talking about electricity in our home energy essentials understandings here. One thing you got to know, you just got to know about electricity is we have a fixed voltage most of the time, and we're controlling the amperage with resistance that we put into a circuit. And everything that's kind of in a circuit provides some level of resistance, and but really we're trying to protect components within a circuit. And so you may have seen these little things called resistors. They have these stripes on them. The goal for today is I'm going to teach you how to read resistors and understand how that controls the current in a circuit. So like I was saying, before we start, actually, let's go ahead and remind ourselves the powers of 10. Let's go ahead and take a peek-see. Remember, when you are dealing with powers of 10, oh boy, a couple little tricks here. Remember, 10 to the second is equal to 10 times 10. So there are two 10s being multiplied. It's also equal to a 1 with two zeros. So the exponent determines the number of 10s in the multiplication, which also determines the number of zeros in your answer. So for 10 to the third, that's going to be a 1 with three zeros, or 10 times 10 times 10. We're multiplying 10 three times, which is a 1 with 1, 2, 3 zeros. 10 is just equal to 10. 10 to the first is just equal to 10. What about 10 to the 0? Okay, remember, with these exponents, how do I get from 1,000 to 100? Well, you divide by 10. So if we're stepping down, dividing by 10, great. How do I get from 100 to 10? Well, you divide by 10. You guys can see the pattern here. So that to go down a step, you divide the answer by 10. To go up a step, you multiply by 10. So then 10 to the 0 is 10 divided by 10, which is 1. In fact, anything to the 0 power is 1, except for maybe 0. Raises some questions. Okay, 10 to the minus 1, we're going to divide by 10 again. That's actually 1 divided by 10 is our answer. And then 10 to the minus 2 is equal to 1 divided by 10 divided by 10. So that would be, if you're thinking math here, 1 divided by 10 over 10 over 1. All right, and so we do, I can't even get the 1 down in there. I'm trying. Okay, what we do is scroll down. Oh, I got it. Look at that. I know what I'm doing. Figured it out. What we do, we can do skip, change, flip, leave the first the same, change division to multiplication, flip the fraction. So really, you can see the power increasing in the denominator. So one direction this way, it's 10. Here, it's 1 over 10. 2 this way is 100. Over here, it's 1 over 100. So it's kind of symmetric about 10 to the 0. One of them, 10's in the denominator. The powers of 10 are in the denominator here and the numerator there. Okay? So this is also a decimal. It's important to remember that's 1/10, and this is 1/100th, which is 0.01, and so it's going to continue from there. 10 to the minus 3 is 0.001, and so forth, so on and so forth. All right, so like I said, most circuits have a fixed voltage. In your house, the plugs that you have or the outlets that you have probably either look like this, like the surprise face, or maybe like this for a dryer or for a stove. So these ones are all 120 volts. Okay, that's just the potential. And then these ones are 240 volts, and they're 240 because you actually, you've got like two breakers supplying them usually. Okay, so these two are 240 most of the time. Okay, and so what we do is we have a fixed voltage. Now, if you want to plug a small device into something like this, you have to make sure, like I said last time, you have to make sure that you have the correct amount of resistance to protect it. So most appliances require a specific fixed current or something close to operate. So like that's what something like an adapter is going to do, right? In order for us to use our wall outlet, it is resistors are the thing that allow us to control the current, which we can take a tiny little LED night light and plug it into the same outlet as a giant refrigerator, and both of them both of them can be used in the same outlet. And it's because this requires more current to keep your food cold than does the tiny LED. But we're adding little tiny things like resistors into the adapters. We're also converting, maybe AC to DC in some of these cases. But you're converting for the fridge. You're converting or you're adding resistance to make sure the current is correct. And that's what we have control over. We have control over the resistance in the circuit. So let's learn how to read them. First of all, what is it? Well, it turns out there are many, many kinds of resistors. There are like carbon film resistors and whatnot, and like metal oxide resistors, and lots of different ways to make them. But the basic idea is you have like an insulative core, and then what you've got is you have this conductive and yet resistive coil that kind of wraps around, so the electricity is forced to travel through there, and you can basically specify the number of windings to control to change the resistance value. Okay, and I'm not an expert on this by any means, but that's the basic idea. So then what you see on the outside, you have the end caps that are kind of conducting the current. What we see is like this protective coating on the resistor. You're not seeing what's happening on the inside. So it says larger pitch means a shorter resistance path, thus lowering the resistance value. And when you lower the resistance value, you increase the current in the circuit. Okay, so here's the basic gist on reading a resistor. This is for a 4-band resistor. There are lots of different kinds of resistors. We're going to start with the easy ones, and we'll go from there. But for a 4-band resistor, you read so first thing you do is you typically look for this kind of a gap, and it's not super apparent here, but there's usually a gap between where the numbers that we read and the 4th band, which is what's called the tolerance. And there's an updated chart later, but it's helpful to look at this one first. So I always align the tolerance stripe on the right when I'm reading a resistor, and you'll know it's the right tolerant, or where which one's the tolerance stripe, either by the gap that's present, or if you see a silver or gold stripe on one side, that's usually a dead giveaway, because the 1st band can't be silver or gold. Okay, so that's a dead giveaway if that's on the right. But look for the gap, look for silver or gold, put that on the right, and that's how we start to read. So with this resistor here, it is black, red, and green. So to calculate the resistance value for this resistor, we are going to do a 0 for black, red is 2, and the 3rd band is what's called the multiplier. So it's what you multiply this number by to get your resistance value. Well, green is 10 to the 5th, or a 1 with 5 zeros. So I can come over to this and do times 10 to the 5th. Well, this is just 2 times 10 to the 5th. That's 2 times 1 with 1, 2, 3, 4, 5 zeros. Or it's a 2 with 1, 2, 3, 4, 5 zeros. So this is 200,000 ohms. And you guys know that, like, when you're writing these down, typically if you're doing some sort of conversion here, how many kiloohms is that? Well, you just divide by 1,000. 200,000 ohms is 200 kiloohms. There's also the prefix mega, which is 1,000 times bigger than a kiloohm, and so this would be 0.2 mega ohms. So taking that and dividing by 1,000 again. So again, it goes ohms, then the next biggest is kiloohms, the next biggest is mega ohms. 1 mega ohm is 1 million ohms. Okay, so we're going to be referencing this chart quite frequently. Let's do some practice here. All right, so here's my resistor. It's already oriented for me. When you pick up a resistor, like a physical resistor, you're going to have to figure out which side is which. We don't have to do that for these problems, maybe later down the road on the lesson. Okay, so blue is 6, Black is 0, and I believe that is brown. Brown is 1. So you're looking at these color codes here, and I have some of them memorized. You're going to probably need this sheet in front of you. So 6, 0, 1, and then there's the gold stripe on the right. So the gold stripe on the right tells us our tolerance. We actually are going to worry about that later. Don't worry about it for now. So the only ones that really matter are the first three. 6, 0, and the number, our multiplier is times 10 to the 1. Well, that's 60 times 10, which is 600 ohms. Okay? Let's go to the next one. All right, red is 2, brown is 1, and our multiplier is 10 to the second, because we put red is 2, right? And we ignore the gold for now. Don't worry about that. So what is this? This is 21 times 100, a 1 with 2 zeros, or 2100 ohms. We could also write that by dividing by 1,000 as 2.1 kilo ohms. Whichever one you think is easier to write. Okay, let's do another one. Ooh, purple. Let's take a look. Purple is, or violet rather, is 7. 7, yellow, so it's purple, yellow, yellow. Interesting. Yellow is 4. So that is going to be 7, 4, and then our multiplier is times 10 to the 4th. 7, 4 times 10 to the 4th, which is 74 times a 1 with 1, 2, 3, 4 zeros, which is 7, 4, and then add 4 zeros. So you can do these pretty fast once you get the hang of it, okay? Put a comma there. That's 740,000 ohms, or 740 kilo ohms. I think kilo ohms makes more sense here as a unit for us to use. Okay, you could also write it as 0.74 mega ohms. I think one of these is the unit that makes the most sense. Okay, next one. Let's see here. Blue is 6. That's a green. And this is black, which is 0, which means we would do times 10 to the 0, ignoring. So just looking at the first three. Well, times 10 to the 0, 10 to the 0 is 1. So this is 65 times 1, which is just 65 ohms. We're done. I think this one is our best bet here. Okay, super. All right, let's look at a couple other ones that are a little harder. Okay, I've drawn some pictures. This is what your homework is going to look like. Some of the questions, some of them are going to be actual resistors that might be rotated a little weird. So I'll give you some challenges there. Red is 2, 2, silver for the third stripe. Let's go back to that chart. This is for 4-band resistors only, right? So the third stripe is the multiplier, and it says silver is 10 to the minus 2. 10 to the minus 2. So this is 22 times 10 to the minus 2, ignoring the gold. Well, 10 to the minus 2, we went over that at the beginning of the lesson. That's 1 over 10 to the second, which is 22 times 0.01 or 1/100th. So you move the decimal place over 2 places, okay? 1, 2 places. This is 0.22 ohms. Okay, how do we write that in terms of a smaller unit? Looks like we're having it in decimals here. We could go down to something smaller, like milliohms, if you wanted to. So multiply by 1,000. That would be 200 milliohms present. Not a whole heck of a lot of resistance there. All right, and green, yellow, gold. You guys go ahead and try this one on your own, see if you can get it. Green, yellow, gold. Here we go. Green is 5, yellow is 4, gold is 10 to the minus 1. So that's going to be moving the decimal place 1 to the left, 5.4 ohms, and I think that's an acceptable unit. Okay, how about if we're trying to read a resistor that has more than 4 bands? Well, here's the chart. And it kind of is, Is that supposed to be red? Boy, that kind of, yeah, I guess that kind of looks red. All right, so basically if you have more than 4 bands, some bands end up having the tolerance. They have an extra stripe for accuracy, and it just depends on what you're reading. What you need to know is kind of what's really important for you to understand are the ones that are to the left. And again, we're looking for that kind of a gap that's present on the larger resistors. This is a 6-band, but the idea is the same. You have several digits, and then you have a multiplier for a 6-band, and then you have your tolerance, and then the temperature coefficient. Okay, so it's like when it's supposed to operate, and so on and so forth. So we're going to be referencing this chart. I'm going to do some harder ones here. Let's take a look at this. Oh boy, it's hard to tell the colors there. I got to be if I'm completely honest. I would call this one brown. This one red. Notice it's kind of backwards here. Yikes. Let's take a look. I guess it is brown. Okay, so this is backwards. You can see the gap right here. So this picture is actually upside down. What I'm going to do is we're going to go ahead and erase that. And we're going to flip this image so that it is the correct direction. So you need to kind of think about this. Flip your paper if you have a question or you're not sure. Don't try and do things upside down, basically. So all these are the same. And it looks to me like our stripes are pinwheeling. All right, perfect. It looks to me like our stripes are yellow, which is 4, blue, which is 6, black, which is 0. Okay, so there's our gap, right? So that means that is our, so I don't think you'll always have to have tolerance. You'll never have just the temperature. You always have to have the tolerance on there. So these are our 3 digits, and then this one is our multiplier. So this is plus or minus 1% because this is brown. So I'm thinking this is yellow, blue, black, and then red, which is times 10 to the second. So this is 460 times 10 to the second. We're adding 2 zeros to that, which is 46000 or 46,000 ohms, which is 46 kilo ohms. Cool. Seems good to me. So that's how you read these resistors, plus or minus 1%. That's our tolerance. Okay, so what does that tolerance, the last band, mean? What it really means is it means that like we're only human, right? When we build something, it's not going to always operate perfectly, and there's going to be some variability in when you make a resistor. So like a bunch of resistors from the same batch, you might have some natural kind of variation. And so what the tolerance stripe tells us, it gives us an upper and a lower bound for where our resistance could actually be operating. So they're saying like when you have a tolerance, you can kind of know like, okay, I know that my resistor is going to operate either between here or between here. Now, if you know that, then you know basically the window of your current. You know, my current is going to be either operating between here and here, and that can tell us whether or not a device is going to could get hurt or could get too much current flowing to it and damaged. Okay, so let's take a look at these. Well, this is the same one, but they have these are 4-band resistors, and we're going to do this together. We're going to find the tolerance for each. Okay, so let's look back. Gray was 8, white is 9. All right, let's take a look. So gray, blue, which is 8. Blue is 6. Purple is times 10 to the 7th. And gold. Gold for the resistance value, I believe, is plus or minus 5%. Okay, and then this is plus or minus 5%. Again, these are the ones that matter. This is 86 with 1, 2, 3, 4, 5, 6, 7 zeros. So that is 860 mega ohms. I divided by 1,000 twice. Okay, so it's 860,000 kilo ohms, which is 860 mega ohms. All right, now that that's done, what does this tolerance actually mean? So this is kind of the center. So it's centered on 860, and it says plus or minus 5%. So I can go here and basically take 860, and we're going to find an upper bound. So there's a couple ways you can do it. You can find 5% of 860, or you can multiply by a decimal that's a little bit larger than 1. So that for the upper bound, which is the higher of the resistance, is going to be 860. So you can find 5% using the is over of equation, or just do 860 times 1.05. Okay, that'll give you an additional 5%. So it could be a little bit higher than that. Okay, and our lower bound on the resistance is 860 times 0.95. That'll give you that, okay? So 860 times 1.05, which means it could be as high as 903 mega ohms, and it could be as low as 60, that's a 9 times 0.95, which is 817 mega ohms. So we have some variation. It's somewhere between between 817 and 903 mega ohms. So what is the thing that we added or subtracted? Well, you'll be able to tell by subtracting these two, dividing by 2, or just finding 5% of 860, which is 0.05. So you do 0.05 times 860, which is 43. Okay, so 43, right? Plus this gives me that, and this minus 43 gives me that value. So there's our upper and the lower bound. I want you to do this on your own. For the second one, again, it's the same resistor, centered on the same 860 mega ohms, except now we have a value of, red there, which is, I believe, plus or minus, a red tolerance value is plus or minus 2%. So let's do that. You're going to find plus or minus 2%, and go ahead and pause the video, do it on your own, and then just watch it in just a minute. I'm going to keep going here. So my upper is going to be 860 times 1.02, and my lower bound for the resistance is 860 times Okay, so we're going to go ahead and go for it here. So that's 860 times 1.02, which is 877. Again, those are mega ohms. And then down here, 877.2. Down here is 0.98 times 860, which is 843, roughly. Okay, 843 mega ohms. So make sure you include units on your answers when you're doing this. I need to see whether you're using mega ohms, kilo ohms, ohms, or milliohms. And I think we got one little bit. So pick one of these. Some of the ones maybe you looked was pretty intimidating at the beginning of the lesson. Look a couple of these and see if you can figure out their values. They're flipped around. So I'm going to do a few, and then you can pause and try and do a couple on your own for practice. There is a simulator online. There's a simulator online if you want to try and get instant feedback before you do your assignment, which I would recommend. So practice the simulator, see if you can get at least 6 or 7 correct, a score of 6 or 7, before you try your assignment. All right, so let's go ahead and do this. This is going to be 9 times 10 to the third, so add 3 zeros. This is 39123, which is 39 kilo ohms, or 39,000 ohms. Okay, this one, gold is on bottom, so look at it this way. You're reading this direction. Yellow is 4, 7, black is 0. This is 47 ohms. This way, brown is 1, green is 5, red is 2. Add 2 zeros. 1500, which is 1500 ohms, or 1.5 kilo ohms. And this is brown, which is 1, black 0, 1 0 with an additional 1. So that's 100 ohms. That's appropriate. 222. That's 2 2 with 2 zeros, or 2.2 kilo ohms. And the last one is 4 7, and orange is 3 zeros. So that's 47 kilo ohms, just like kind of like the first one. Has the same multiplier. All right, guys, thanks for watching. Hope you learned something. And yeah, look forward to seeing you in class. See you guys later. Bye.